Hello everyone, this is Jesse Crawford with New York Medical College, and this is the first lecture video for the course, which is an introduction to statistics. Let's start with a quick introduction to what statistics is. Statistics is essentially the study of data, more specifically the study of data collection, organization, presentation, and interpretation. This can be broken down further into descriptive statistics, which involves the organization and presentation of data, and inferential statistics, which involves the interpretation of data. It may not be obvious why statistics is important to the medical field or to public health, but there are actually many situations where statistics plays a role in these fields. The most obvious example would be a clinical trial. If you're trying to do an experiment to determine the impact of a medicine or a vaccine on a disease, it's important to be able to analyze that data rigorously, and statistical techniques can be used to do that, and we'll talk about some of those techniques in this course. Or what if you just have a large data set consisting of a bunch of different risk factors for a disease, and you want to try to build a statistical model to predict which of these risk factors has the biggest impact. These are just a couple of examples of how statistics plays a role in the medical field. We'll actually cover descriptive statistics, which is the organization and presentation of data, in topic 2, and then most of the remaining topics for the rest of the semester will really focus on inferential statistics, which is just when you have a lot of data available to you, how can you analyze that data to draw accurate conclusions from it? But today's lecture is just going to go over some of the introductory concepts and vocabulary in statistics. A situation that occurs a lot in medical studies is looking at two different variables and trying to see if there's a relationship between them. For example, you might be interested in seeing if smoking causes lung cancer, and we're all aware of the fact that it does, but there was a point in time when people didn't know this and they had to figure out whether that was the case or not, and in order to do that they had to look at data and use data to draw those conclusions. So we're trying to figure out if smoking causes lung cancer. Another way to put that would be to say, does smoking have a causal impact on lung cancer? And there's some terminology that goes along with this type of situation when you're trying to see if one variable influences another variable. We're going to call smoking an explanatory variable, and we're going to call lung cancer the response variable. So you might say smoking explains whether or not someone is going to get lung cancer or not, and then you could say that lung cancer is a response to smoking. Of course, smoking isn't the only variable that has an impact on lung cancer, but it is one of the variables that does. Another term for smoking here would be an exposure variable, because someone who smokes is exposing themselves to the risk of developing lung cancer. Or you might call lung cancer an outcome variable, because it's one of the outcomes that can result from smoking. Here's another example where we're interested in the relationship between two variables, except here we're trying to see if a newly developed cholesterol medication has a causal impact on someone's cholesterol level. Again, we're using the terminology of explanatory variable for cholesterol medication and response variable and outcome variable for cholesterol level. On the previous slide, we called smoking an exposure variable, and you could call cholesterol medication an exposure variable, but it's really more accurate to use the word treatment variable because this cholesterol medication is a treatment that's intended to control someone's cholesterol level. There are, broadly speaking, two types of studies that can be used to determine the relationship between two variables. The first is an experiment, which is where an investigator actually determines which subjects receive a treatment and which subjects do not receive a treatment. In an experiment, the investigator plays an active role in controlling what's happening in the study. On the other hand, there are observational studies where an investigator simply analyzes existing data. So in an observational study, the investigator plays no role in what's actually happening to the subjects. The investigator simply takes data that already exists and analyzes it. Okay, let's take a look at how an experiment works in a little more detail. A moment ago we were talking about trying to figure out whether a newly developed cholesterol medication has an impact on someone's cholesterol level or not. In order to use an experiment to figure this out, we would start off with a group of volunteers, and we would divide them randomly into a treatment group and a control group. The purpose of dividing them randomly is this actually helps to ensure that the treatment group and control group are very similar to each other, and that will mean that any difference between the treatment and control group's cholesterol levels can actually be attributed to the cholesterol medication and not due to some other variable that we haven't taken into account. So we give the treatment group the cholesterol medication, and we give the control group placebo, which is a fake medication. The reason to give a placebo is because of the placebo effect. The placebo effect says that if you give someone a medication, whether it's real or fake, it will have kind of a psychological impact sometimes, and it can actually lead to relieving their symptoms to some extent. So we want to make sure that the difference between the treatment and control group is a real effect and isn't just the result that the treatment group is receiving a medication, getting the psychological boost, and the control group isn't getting the psychological boost. We don't want that to happen. So to kind of go over the framework again, we take a group of volunteers, we divide them randomly. That ensures that the groups are going to be very similar with respect to all variables. We're giving the treatment group a cholesterol medication. They're going to get the psychological boost from receiving a medication. We're giving the control group a placebo. They're going to get a psychological boost from receiving a medication because they don't know it's a placebo. They don't know whether it's a real medication or not. So the only difference between the treatment group and the control group is the treatment group actually is getting the cholesterol medication and the control group isn't. Then we can look at the change in cholesterol for the treatment group. We can look at the change in cholesterol for the control group. And if there's a statistically significant difference between those, which we can determine using statistical techniques that we'll discuss later in the course, then we can infer from that that this cholesterol medication really does have an impact on cholesterol. And this brings up the subject of blinding in a study. So on the experiment on the previous slide, we talked about how some of the patients were getting cholesterol medication and some of the patients were getting a placebo, but the patients don't actually know what they're getting. So in that sense, they're blind. Now, you can also have a study where the doctors involved in examining the patients don't know who received the treatment and who didn't either. This is called a double-blind study. And this could be really important, say, if you're doing a study involving cancer, where some doctors are having to look at complicated images from MRI or something like that. In some of those cases, the doctors have to make subjective judgments about whether a patient is developing cancer or not. And if the doctors know who received the treatment and who didn't receive the treatment, this could actually bias their responses. So whenever possible, you do want to try to conduct studies that are single blind or double blind when appropriate. Now that we've talked about experiments, let's look at observational studies in a little more detail. In the experiment that we were just discussing, an investigator was trying to figure out whether cholesterol medication had an impact on cholesterol level or not. In order to do that, the investigator took a group of volunteers and divided them into a treatment group and a control group. The investigator gave the treatment group a medication and gave the control group a placebo. In other words, the investigator played an active role in that study. Now, by contrast, an observational study is just when an investigator takes data that already exists and simply analyzes that data in order to draw conclusions from it. Now, you might say, why would you ever want to do an observational study when you could do an experiment? And the problem is there are a lot of problems where you can't do an experiment. So, for example, if you were trying to determine whether smoking influences lung cancer or not, you can't do an experiment where you give people a bunch of cigarettes and give other people a placebo and try to figure out the impact on lung cancer. That wouldn't be ethical. So sometimes it is necessary to perform an observational study. We simply collect data on a large group of people through various agencies that may have access to this data, and then we compare smokers and non-smokers and see if smokers are getting lung cancer at a higher rate than the non-smokers. Now, this can result in some problems because there might be other differences between smokers and non-smokers that could have an impact on whether or not they're getting lung cancer. One important variable is age. Older people are more likely to smoke than younger people, and older people are also more likely to get lung cancer than young people. There can also be some differences with respect to variables like gender, ethnicity, and possibly other variables that we might need to take into account. So one method to try to deal with this is something called homogeneous classes. So the word homogeneous just means similar. So you try to break people down into different groups that are very similar to each other, with the only difference being that one group smokes and the other one doesn't smoke. So, for example, you might compare white female smokers 30 to 39 years of age to white female non-smokers 30 to 39 years of age. Or you might compare Latino male smokers 20 to 29 years of age to Latino male non-smokers 20 to 29 years of age. And this will help you to figure out if smoking is having an impact on lung cancer. Another technique would be to construct a statistical model that predicts lung cancer based on a variety of risk factors, including smoking, and then you could look at various quantities in the model related to smoking, which would help you figure out whether smoking was actually having an impact on lung cancer or not. And constructing statistical models is one thing that we are going to talk about later in the course. On this slide, we're going to look at another example of an observational study, which will introduce the concept of a confounding variable, which is one of the problems that observational studies can have. We're going to be talking about the disease pellagra, which was a disease that existed between the 18th and 20th centuries, and it caused pretty significant physical and mental deterioration. Now, one cause that people thought might influence pellagra was the presence of certain flies. They were blood-sucking flies, and people were worried that these flies were actually spreading pellagra among different people. And people noticed, for example, that homes that had a lot of these flies had more cases of pellagra, and homes with fewer cases of these flies had fewer cases of pellagra. So does this information actually show that these flies are causing the disease pellagra? Well, the answer is no. The problem with the discussion that we had on the previous slide is we weren't taking into account all of the variables that have an impact on pellagra. And it turned out, through a study in 1914 by Joseph Goldberger, that the variable that had the biggest impact on pellagra was a lack of niacin in the diet. So the reason that it looked like flies were causing pellagra is because people that were in poverty tend to have less sanitary homes, and those homes had more flies in them. But the people in poverty were also likely to have a poor diet consisting of a lot of corn, and they weren't getting enough niacin in their diet, and that was causing them to get pellagra. So to recap, people were trying to see if there was a relationship between the presence of flies and pellagra. Poverty was indirectly related to flies being in the home. Poverty was also indirectly related to pellagra, and so since poverty was influencing flies and influencing pellagra, it looked like there was a causal relationship between flies and pellagra when there really wasn't one. So this is an example of something called a confounding variable. A confounding variable is a variable that's related to an explanatory variable and is related to the response variable in such a way that it makes it look like there's a causal relationship between the explanatory variable and the response variable, but there isn't really one. And this is why it's so important to do experiments when we can. Because when you do an experiment and you randomly divide your volunteers into a treatment group and a control group, you automatically make the treatment group and control group very similar with respect to all variables. So it actually eliminates the possibility that a confounding variable can exist. Or if you can't do an experiment and you're forced to use observational data, it's important to use one of the techniques that we discussed on the previous slides of homogeneous classes or building a statistical model so that you can take into account the other variables that are relevant in the study, so you don't have this problem of a confounding variable distorting the results of your analysis. This slide talks about the difference between quantitative, categorical, and ordinal variables. And these variables are actually exactly what they sound like. A quantitative variable is a variable that involves quantities or numerical values. So something that you can measure and actually get a number for. So something like blood pressure, age, temperature, or cholesterol level, those would all be examples of quantitative variables. On the other hand, a categorical variable is a variable where you're dividing people into categories. So for example, gender, you're looking at the categories male and female. Ethnicity, you're going to be looking at several different categories. Or you could be talking about blood type, eye color, marital status. In each case, you're just talking about taking a group of people and dividing them into a bunch of different categories where each category has some label associated to it, but you're not actually talking about assigning a numerical value to someone. Finally, we could talk about ordinal variables. Ordinal variables are also categorical variables where you're looking at categories, but it's where the categories have a natural ordering associated to them. So, for example, you might be talking about t-shirt size. I can have a small, a medium, or a large t-shirt. Now, these are just three different categories of t-shirts, but there's also associated an ordering. A small shirt is smaller than a medium shirt, and a medium shirt is smaller than a large shirt. Or, for example, survey answers. When you give people surveys, typically the results are strongly agree, agree, neutral, disagree, strongly disagree. something like that. And again, these are just different categories for the answers, but they have a natural ordering associated to them, so that's what makes that an ordinal variable. All right, the last thing that we're going to talk about in this lecture is the concept of relative frequency, and we'll look at a couple of examples to talk about this. So on this first slide, we can see it says we have a table of heights for a sample of people. And these heights are measured in inches. So we've got heights ranging from 60 to 71 inches. Now the first question, it says, how many people are represented in this table? The answer is 12. We've got 12 numbers up there. Each of these numbers represents the height of one person, and so we've got 12 people. And then it says, find the relative frequency of heights from 60 to 62 inches. Now relative frequency really just means percentage. Whenever someone says find the relative frequency of a certain range, they're just saying what percentage of the subjects in your sample are in that range. So you can see that we've got 3 numbers from 60 to 62, and there's 12 total people. Well, 3 divided by 12 is 0.25, or we can express that as a percentage and we get 25%. So the answer to that second question is 25%. Then it says find the relative frequency of heights from 63 to 68 inches. Well, we've actually got 6 numbers from 63 to 68, and 6 divided by 12 is 0.5, or in other words, that's 50%, and so the answer to that question is 50%. This last slide also deals with relative frequency, but the table that we're working with is a little different. We have an age column with ages from 21 to 25, and we have a frequency column with a bunch of frequencies. Now on the last slide we said that relative frequency represents percentages. So if relative frequency represents percentages, what does frequency represent? The frequency of an observation is the number of times that observation occurred in the data set. So for example, there's an 8 next to 21. That means that there are 8 people in the data set that are 21 years old. There are 12 people in the data set who are 22 years old. There are 15 people in the data set who are 23 years old, and so on. So the relative frequency of an observation is the percentage of time that observation occurred. The frequency of an observation is the number of times that observation occurred. Now if we look at the questions to the left-hand side of the slide, the first thing says, how many people are represented in this table? Well, we know how many people are in each category. There are 8 people who are 21, there are 12 people who are 22, and so on. Well, that means if we want to know the total number of people in the set, we just need to add up all those frequencies. So if you add up all the frequencies from 8 to 5, you get 50. So there are 50 total people in this sample. Second question says, what is the relative frequency for the age 21? Well, again, relative frequency represents percentage. If we want to know the percentage of people who are 21, we take the number of people who are 21, which is 8, and we divide that by the total number in the data set, which is 50. 8 divided by 50 is 0.16, which is equal to 16%. So the relative frequency of 21 is 16%. Third question, what is the relative frequency for ages 22 through 24? Well, the first thing we have to ask ourselves is how many people are between the ages of 22 and 24? Well, that's going to be 12 plus 15 plus 10, which is 37. So the number of people in the sample between the ages of 22 and 24 is 37. The total number of people is 50. 37 over 50 is 0.74, and so that means 74% of the sample are between the ages of 22 and 24. The last question is similar, but it's talking about the relative frequency for ages between 21 and 25. So we're going to do this the same way, but now we're actually going to add up all the frequencies in the table, and that's going to give us 50, and then we divide that by the total number, which is also 50, and we get 1, or 100%. So this means 100% of the people in the sample have ages between 21 and 25, but that makes perfect sense because the ages from 21 through 25 are the only possible ages in this table. So that's it for our first lecture in the biostatistics course, guys. I hope this lecture was helpful, and I just want to close by saying that if you have any questions, please do not hesitate to ask me. You can always email me or send me a private message in the online course system. But another option is you can post a question in the homework and lecture help forum. And this is probably one of the best ways to ask a question because that way everyone can see the question, everyone can see any answer that I respond with, and also it raises the possibility that other students can respond and help you out that way. But again, please don't hesitate to ask if you have a question, and I'll see you next time.